So here's an explanation of Newton's third law. There's something I think quite important in this video, in that I think there's a misconception that causes confusion among students, which I hope this video will help with. Newton's third law is a contact force law. If object A comes into contact with object B, it exerts a force on that object B. But equally, B exerts a force on A, and that force is equal in size and opposite in direction. So when two things come into contact with each other, they exert an equal but opposite force on each other. So to illustrate that point, if you're on an ice rink and you've got ice skater A pushing ice skater B in the back, you'd expect ice skater B to move to the right, as the diagram shows. However, if A is exerting a force on B, Newton's third law says at the same time B must be exerting an equal force on A, but in the opposite direction. Therefore, this will happen. Not only will B move to the right because of the force exerted from skater A, but skater A will move back to the left because of the opposite force that B has exerted on it. It's an equal and opposite force, equal in size but opposite in direction. I want to take a moment to explain something about weight, which I think is really important, and a concept that I think is misunderstood by students and causes confusion. Hopefully this will explain it clearly to you. So we have a person standing on the table, and if we were to put forces on this diagram, well, there would be a weight of the person that we could immediately put on that diagram. Now, lots of people would say, well, that weight acts on the table. So the weight of the person is acting on the table. I want to take a moment to explain why in actual fact that's wrong. And I want to explain why it's wrong, so if you thought that was the case, you'll have a better understanding. The weight of an object acts only on the object. Now you might be thinking, well, hang on a minute, if I stood on a pair of bathroom scales, then it would show me my weight. Well, it would show you mass, wouldn't it? Therefore, my weight must be acting on the scales. So you'd stand on the scales, it would show you 765 newtons, which is the average weight of a UK adult. And you would be saying, well, that's my weight acting on the scales. And then your scales would convert that into kilograms, and that would be 78 kilograms. However, what I want to say to you is that in actual fact, what your scales are showing is not your weight, but your contact force. You are in contact with the scales, and therefore you are exerting a contact force on the scales, and the scales are exerting an opposite contact force that you will feel on your feet. Now, if you were in a lift, standing on your scales, and the lift was accelerating downwards at 2 meters per second squared, in actual fact, you wouldn't see 78.0 kilograms on your scales. You'd actually only see 62.1 kilograms. Now, clearly, your mass has not changed, but what is showing on the scales has changed. Therefore, that calls into question, is the number that's shown on the scales really your mass? And if you're accelerating at 2 meters per second upwards in this lift, then what your weighing scales would be showing would actually be 93.9 kilograms. So it can't be that your weight has changed, it can't be that your mass has changed through this motion, but it can be that the normal contact force between you and the scales has changed. And that's what is being shown. It's a normal contact force. If a person is standing on the floor, obviously they're in contact with the floor, so there's going to be a contact force. That person receives a contact force from the floor, they can feel that under their feet, and therefore the person will exert an equal and opposite reaction force on the floor. Therefore, what the floor feels, as it were, is the reaction force, not the weight of the person. So there's the person, there's the weight acting on the person only, and the person receives a contact force, so that it's saying the reaction force on the person from the floor. Meanwhile, the floor receives an opposite but equal contact force from the person, so that's a reaction on the floor from the person. And these two forces are equal to each other. And when the person is stationary, then the contact force that the person feels will equal the weight of the person, and therefore the weight of the person will equal the contact force that the floor feels. But that is different. Saying that the contact force that the floor feels is equal to the weight of the person is just subtly different from saying the weight of the person acts on the floor. It's the weight of the person that is creating this contact force. So here's our example, which refers back to a previous explanation of somebody in a lift, 78 kilograms, accelerating downwards at 2 meters per second squared. So let's look at the forces on the person. Straight away, the person's weight, so that's 78 G newtons, and the reaction force on the person from the floor of the lift, which we've labelled R. The lift is accelerating downwards, so the resultant force on the person is this 78 G downwards minus R, which is acting upwards. So that resultant force equals the mass times acceleration, and when we rearrange that, we find that R equals 608.4 newtons. Now that's the force. Now that's the force on the person. That will also equal the force on the floor from the person, because it will be an equal and opposite force. And if we divide that by 9.8, that's equivalent to 62.1 kilograms of mass, which you recall was what would show on the scales if you were standing on the scales accelerating downwards at 2 meters per second squared. If you want to check your understanding of this, if you want to calculate what would be the size of the force exerted on the person if the lift was accelerating upwards at 2 meters per second squared. Remember, the answer to that on the scales was 93.9 kilograms. See if you can work that out and get 93.9 kilograms. Remember, you'll be calculating a force, so your answer will be in newtons, and you'd have to convert that into the equivalent mass by dividing by 9.8. Here's a second example highlighting the point with Dick Dastardly taking a ride in a hot air balloon, watched closely by Muttley, and the balloon is accelerating upwards at 2 meters per second squared. Okay, we're asked for the size of the force that Dick Dastardly exerts on the floor of the balloon. That's exactly equal to the force that the floor of the balloon exerts on Dick Dastardly. They're equal and opposite forces. So let's look at the force exerted on Dick Dastardly. The first force I would always mark on is the weight of the object, in this case the weight of Dick Dastardly, and he's receiving a force upwards from the floor of the balloon. He's accelerating upwards at 2 meters per second squared, so the resultant force will be R upwards minus 70 G downwards. and that equals mass, which is 70, times the acceleration, which is 2. And then when we rearrange that, we find that R equals 826 newtons. That's the force on Dick Dastardly. It will be equal and opposite to the force that Dick Dastardly is exerting on the floor of the balloon. Here's an example from a textbook where we have two objects stacked on top of each other, and it's in a pan, and there's a string, and the whole thing is accelerating upwards at 0.5 meters per second squared. So if we just take the whole object as one mass, we've got the weight, which is the 400 grams and the 600 grams, that's a kilogram, so that's 1 g newtons of weight, and upwards there's a tension in the string. The pan itself is light. It will have a mass, but the mass is small compared to other masses in the system, so it's negligible. Therefore, the resultant force, because this is accelerating upwards, will be T minus G. So using Newton's second law, T minus G equals the mass, which is 1, times the acceleration, which is 0.5, and we get 10.3 newtons for our value of T. For part B, find the force exerted on mass B by mass A. Well, I'm going to look at the force exerted on mass A by mass B, because it will be equal and opposite to the force exerted on B by A. So I'm just looking now at object A. It's got a weight of 0.4 g newtons, and it has a reaction force from B. So imagine that you in fact were object A. You could feel something under you, and that would be the contact force from object B. So this is a contact force on A from object B. Now, what is object A doing? It's accelerating upwards at 0.5 meters per second squared. So the resultant force is this reaction force subtract 0.4 g. And that equals mass times acceleration. Mass is in kilograms, so it's 0.4. And we get 4.12 newtons. So that is the force on A exerted by B, which is equal and opposite to the force on B exerted by A. And that's what we were being asked for. Still 4.12 newtons. In part C of the question, we're finding the force exerted on mass B by the scale pan. So there's mass B. Its weight is 0.6 g newtons. Mass B is in contact with the floor of the pan, so it's receiving a contact force from the pan. So that's the force on mass B from the pan. But it's also in contact with object A, and we've already found out or calculated that the force that object B receives from object A was 4.12 newtons. So now the object is accelerating upwards at 0.5 meters per second squared. So we have one positive upward force and two downward forces, so they've been negative. So when we're applying Newton's second law, we've got the upwards reaction force minus the weight minus the reaction force or contact force from object A equals mass of the object times the acceleration. And that gives us 10.3 newtons. So I hope this video has emphasized to you the importance of understanding that weight acts on the object only, and any other force will be a contact force between an object and something else.